Welcome to the University of Hawaii Institute for Astronomy Haleakala Division. I'm Dr. J.D. Armstrong. I'm the Maui Technology Education and Outreach Specialist. One of the things I get to do is put together these talks and drag these wonderful people in to come and talk about their research. This week, this month, we have Dr. Hiromu Nakagawa. Did I get close? Good. He's from Japan, the University of Tohoku. He received his PhD from the Department of Geophysics, and he's interested in terrestrial atmospheres. So the Earth's atmosphere, Mars's atmospheres, or Mars's atmosphere, but atmospheres in general. He's the instrumentalist for a telescope which has been installed at the summit here on Haleakala. He specializes in infrared and spectroscopy mostly, correct? And I will turn the time over to Hiromu. Let's give him a nice Maui welcome. Okay, let's test the volume.
Okay.
So if you put that on your ear.
Ear?
Yeah.
Like this?
Yes, I think. However it works.
I guess
Okay.
it works. Okay, thank you for JD for perfect introduction.
Well, thank you. If they ask questions, please repeat them.
Okay, I repeat the questions. Okay. And thank you for your participating this meeting. And first of all, it's a pleasure to let you know it's 3 years has passed. No. 30 years has passed since our observation at this Haleakala was initiated in 1988 by Professor Sho Okano. He's over there. I'm very proud of such very long good collaboration between Maui and Japan. 30 years, very long time. So also I have just started to stay here 1 month, but I plan to stay 2 years to set up the instrument and get the new facts about Mars. With this telescope, now we have our dedicated telescope called T60 because very small 60 centimeter telescope, but very specific for our observations. At the summit, just in this week, we have finished to set up the telescope and this instrument, thanks to the great collaboration with University of Hawaii. So maybe we got the first light of this telescope in the next week, I hope. I really wish. So this is the title of my talk today, Remote Sensing of Martian Life Evidence from Haleakala. Sounds big issue, but try to discuss with you. This is old picture from Rowell. For decades, people speculated that bright and dark areas on Mars were patches of vegetation, plants, and or channel in the disk of Mars. Mars was a likely place for advanced life forms, and water might exist in the polycaps at that time. When Mariner 4 is the first spacecraft for Mars, flew by Mars in 50 years ago, photographs of the bleak crater surface shocked many people. Mars seemed to be a dead planet. But later missions, recent aggressive missions, showed us that Mars is a complex planet and holds many mysteries. I mean, the open questions yet to be solved. So this is what I want to say today for you. Mars environment is severe. However, some microbes can potentially survive in Martian-like environment. Simplest organics the methane has been detected in the Martian atmosphere 10 years ago. But still, this existence under debate. Why? You may know after this talk. Does such a life really exist? And what can we do from here? This is an outline of this talk. First, you think about the life on Earth. And chapter 2, you think about the life on Mars. And finally, I would like to introduce my instrument and advantage of Haleakala. Actually, first part is the review. I would like to review the very interesting story of my colleagues in Japan. Aura tells us who protects us in the universe. And Mars environment, how severe it is, but still may good enough for some microbes. And we have ultra-high resolution spectroscopy at the summit. How to find evidence, it's my part. So let's move on to chapter 1. 3 shears, the barrier for us. Have you ever thought how to connect between Earth and space? This is a view from the ISS, And the aura itself is visible interface between atmosphere and space. Actually, it looks like a cocoon which protects us. I would like to remember there are 3 to produce aurora phenomena. This is the sun in the visible range, what we can see. Very flat and stable looks like, and sometimes we can see the dark sunspots over there. When sun has when we see the UV range, it looks like very more drastic and active, and so many eruption and flares, so significantly different in the visible range, because so many complex magnetic field in the solar photosphere. This photosphere originated from here or under the photosphere, expanded to the space far from the sun toward our planets, and of course interplanetary space, actually field in our solar system. And along these lines, a large amount of solar wind plasma flow out into the space. This velocity is 300 to 800 kilometers per second, very high.
So are those photons, or what are those?
Protons or some high energy particles, and of course electrons is also included. First, they reach to the Mercury. Mercury has an actual weak magnetic field, but not the atmosphere. Mercury can't occur the aurora. Next is Venus. Venus has a dense atmosphere, 100 times denser than Earth, but no magnetosphere. That's why solar wind and Venusian atmosphere interacts directly, like this. Next is our planet, the Earth. The Earth has very large dipole magnetic field. It calls a magnetosphere. which interact with solar wind plasma flow before the solar wind to reach our atmosphere to block, and after interacting, the solar wind plasma and its energy are restored in the tail part in the magnetosphere. It's very complex interaction, and it's still going on to understand. But sometimes our solar wind plasma led into the magnetosphere along to the magnetic field, and sometimes accelerated magnetospheric particle accelerated by the solar wind. And finally, they hit the atmosphere to put on their energy on the atmosphere. And atmosphere release its energy because too high for them. That is aurora phenomena. And of course, aurora tells us components, because green aurora indicates oxygen, which plants caused, life caused. So now you know there are three for aurora. One is solar wind, and next is magnetosphere, and third is the atmosphere. And I would like to make you remember these three are also important for our life. I explain. Next slide. This is a sealed one solar wind. As I said, our expanded solar wind forms heliosphere, where is the region of the sun dominance. And finally, solar wind plasma reach to the interstellar space and interact with the interstellar medium. Owing to the solar wind flow, our interstellar plasma flow and cosmic rays, which is originated by the supernova or something like that, cannot penetrate into the heliosphere so much. This is the evidence to show the role of the solar wind. This is a year, and this is red is a sunspot number, and over there is a neutron number. This means cosmic ray flux measured on the ground. If the sun increased its activity, the cosmic ray measured in the ground is significantly decreased like this, and vice versa in the late 6 years. This is very clear anti-correlation ship, because solar wind magnetic field prevents cosmic ray penetrating and to reach our planets. If we don't have such huge solar wind magnetic field, I mean by encounter some galactic activity, for example supernova very close to us, and or encounter with the dark clouds, it may shrink our heliosphere. It caused, for example, cosmic ray flux increasing, and after that cosmic ray makes the nitrogen oxide family, which destroy the ozone layers, and of course sometimes may produce more clouds, which cause the global cooling. This sounds not so good for us, but anyway, as the present Earth it's so many seals for Earth. Second is magnetosphere. Sun actually protects us, but on the other hand, Sun itself emits a large amount of plasma flow, as I shown before. And of course, high energy particle. This is a Earth size, very large size eruption accompanied with such kind of coronal mass ejections. This kind of noise is a high energy particle from that eruption to reach the satellites. Of course, to reach the Earth. But we have a magnetosphere to avoid them. So such kind of high energy particle can never reach us. On the other hand, Mars does not have such kind of magnetosphere. That means Martian atmosphere easily to be removed like this. This is a numerical simulation of my colleagues. But such kind of direct interaction between solar wind and atmosphere cause the significant escape of water and the atmosphere. Series 3 is the atmosphere. This is the result of Dr. Hess in 100 years ago. He ride on the balloon like this, and surprisingly to reach the 5,000 meter altitude without any oxygen masks or yeah, that's so amazing. But over there they found he found the cosmic rays increased at the high altitude. So he concluded the cosmic rays is from sky, from the space. He got the Nobel Prize by this work. Actually, atmosphere prevents the such high energy gamma ray and X-ray, and the ozone layer prevents ultraviolet flux like this. And actually some portion of infrared lights can never reach to the ground because of the absorption of the terrestrial atmosphere. That's why we sometimes got the spaceborne telescope in the ultraviolet, infrared, and X-ray gamma ray, because we could never see from the ground. Actually, when we have ozone destruction, the ozone hole, this is the annual variation of the ozone hole, we got the UV flux even in the ground, which may our gene should be damaged if we got the high level UV flux. That's why we have to concern about that ozone hole. Actually, ozone is also connected to the oxygen. Oxygen is very important for the life. Oxygen and ozone layers play a very important role in our history on Earth, in particular to increase the species. But in Mars' case, he doesn't have ozone layers. Actually, Mars, there is a very tiny ozone amount, but it's not so good enough to make the layers. This is a vertical profile of the temperature. This is the Earth, and this is our Mars. And because this enhancement of the temperature around this altitude, because due to the absorption of the UV by ozone, but we cannot see in the Mars temperature profile. So this is a summary of this first chapter. We are protected by 3 seals. Now you know, on Earth, solar wind, magnetosphere, and atmosphere. But not for Mars. Solar wind, actually, yes, but no magnetosphere, no ozone layer, and no dense atmosphere. So you see, a Mars environment should be severe. So let's move on the next chapter. Is there any possibility to survive in such severe environment on Mars? How do you think? We got to answer somehow. This is Mars. This is Mars. How do you feel? Looks no life for me. Then how about the next one? How do you feel? How do you feel? This is Atacama Desert in Chile. Amazingly, it is 5,000 meter altitude desert with a low temperature, low pressure. Precipitation is almost zero. It looks like Mars environment. Looks no life too, but my colleagues took the soils at these sites and tried to get the measurements by his equipment. Then so many microbes over there, such in cold and dry desert. This is some kind of microscope, and these green spots, all green spot is microbes. So now we know, still in such a severe condition, we could have many microbes. So think more about Mars. Size of Mars is almost half of that of us. So gravity is just only 60 less gravity. Actually, gravity is very important for growth of large animals and plants, but has not influenced so much on microbes. As for the temperature, as you know, Mars is very cold, but distributed in this range. Sometimes above the water freeze level. Very cold, but the high temperature situation on Mars is still good enough to increase microbes. Significantly difference between them is the atmosphere. Just only 0.75% on Mars against our atmosphere. I mean, the over 100 times denser than Mars atmosphere, Earth is. But microbes were recently found which can increase in these conditions. And how about CO2, carbon dioxide? It's not so problematic for the microbes. This is also the recent results. This is the possibility of life on Mars. Gravity, yes. Temperature, no problem. Pressure, okay. And atmospheric components, good. And how about the gamma ray? This is actually high value than what we have. But actually, it's not good for us, but no problem for microbes, my colleague said. So I think most problematic issue is the UV flux. This value is very, very strong. Maybe several minutes is good enough to kill microbes. So it's dangerous on the surface. But still, possibility is underground. Several centimeters is good enough to prevent such UV flux. So answer is yes. Of course, when we concern and assume about the life on Earth, some microbes can potentially survive in Martian-like environment. I think that it's surprising for me. So what does the life need to survive? What do you want? Yeah, almost done. Almost done. Food and water and oxygen. Yes, talk about the water. I want water, even on the Mars. Scientists believe that Mars experienced huge floods about 3.5 billion years ago. We do not know, nobody knows, where the ancient fluid water came from, which creates such kind of geological feature, and how long it lasted, and where it has gone. Our scientists know anything. But, yes.
How do you know it was water that was there?
It's many evidence about the geological feature and some, how to say, shape of rocks.
Couldn't it be a liquid? Wouldn't necessarily have to be water?
It's yeah. Actually, this was. Sorry. Repeat the question. Question is, what is the evidence of the liquid water? In my memory, it was hot topics is under debate, but recently, scientists believe these structure and minerals, I mean the components are investigated by the landers and rovers. These results showed water, liquid water. I mean I'm not sure the name of material, but such kind of measurements tell us. Sorry? H2O, yes. Or, okay, I'll later, maybe in the next slide or next slide, I put some other information. 2002, Mars Odyssey spacecraft have discovered very interesting hints about this issue. That spacecraft indicated large quantity of water ice close to the subsurface. What I mean is, this is a map to be made by Mars Odyssey, neutron measurements, neutron from the hydrogen. So blue color corresponding to the hydrogen-rich deposit, just maybe a few millimeters from the surface. Surprising is we could find hydrogen, such kind of a hydrogen-rich region even in the equator. So substantial subsurface layers of frozen water could be potentially exist. Actually, at the footprint of the rovers, we could see the frozen water like this, and the flash crater accompanied with frozen ice. but due to the low pressure, it should be evaporated like this. Actually, in the today's Mars, very active water cycle in between the atmosphere, regolith, and the polar caps. So we have to know more about that. This is another evidence about that. This is a picture took for 6 years later and before and after. And we could find a new deposit like this. I want to say our potential seepage from the ground. Of course, I said due to the low pressure, it's difficult to keep the liquid condition. But looks like the liquid behavior. Some scientists suggest I forgot how to say in salt. Some play a role to keep like this behavior, but nobody know the detail. See going on the hot topics. Yeah, we could find another samples, but interesting things is Oze and Sharma 2005 suggest the stable liquid water layer in 2 to 25 kilometer depths from surface with the temperature condition is 20 to 300 degree. If this is real, this is very good for reaction to make organics and some interesting chemistry. Now, of course, liquid water itself makes sense. Next is organics. I mean the food for microbes. Maybe you know these topics because long time story. Simplest organics, methane, CH4, has been detected in the Martian atmosphere 10 years ago. And this is maps of the intensity of the methane emission. And this is our seasonal variation. Vertical is a latitude. And point is the localized source in the several kilometer region and fast lost in the range of years. It was so amazing, but because our understanding of photochemistry on Mars condition, Mars should be kept in 300 years. So something strongly kill the methane. Otherwise, we can never believe such kind of variations. Why so hot topics about methane? Because 90% of methane on Earth is originated by the biological source. Our rest is volcanic or, the geological source. So then, what is the source of methane on Mars? This is still going on. Nobody knows. But now you know potential water layer here and some abiotic reaction may be possible with microbes. But since 2009, 2009, nobody could detect methane signal. Recently, very huge, excellent lander, Mars Science Laboratory, tried to find the methane. And he could not find the methane signal at its landing site, gas crater. But on the other hand, SO2 and H2S were found. This is also good food for microbes. So like this, H2S and SO2. And the interesting thing is O2 could be evaporated from the rocks. Anyway, so this is the final chapter. How to find evidence. How can we do about these topics from the summit of Mount Haleakala? This altitude is good for infrared spectroscopy because less absorption of the atmosphere. Of course, good for continuous monitoring using the telescopes. Subaru telescope or Mauna Kea and other NASA big telescope is difficult to use daily use because of its public use. But it's difficult to understand, for example, the Earth by 1 day measurements per year at one location. It's very difficult. So we use infrared, this electromagnetic waves. I explain why. This is the sun, and this is the Earth, and this is Mars. Earth, Mars, Sun emits for lights. I mean the sunlight invisible, illuminated from the sun, which heat Mars and Earth, and then Mars and Earth emits infrared radiation. This is a Wien's law. People call the Wien's law. This is the shape of the radiation of the heated body. Sun is very hot, 66,000 Kelvin, like this, so its peak is located around the visible range, 300 nanometer to 700 nanometers. On the other hand, Mars and Earth is good for our life, around 200 to 300 kilometers. Its peak located around 10 micron or 20 microns. So 10 micron measurements is maybe very suitable to get some signal of habitable planets. So think about this condition. If the spaceman observes the Earth's infrared emission, how should be there? This one. This is the shape of the infrared. We call the Planckian functions. And this continuum tells me the temperature of the planets. And you can see also the dip here and here and here. Because in infrared region, so many molecules which has individual absorption lines. So this position should never change. Then we can see the absorption, I mean the decrease of the intensity of the emission. Now spacemen know, oh, this planet has a CO2 and water vapor and also ozone and methane. Now he sure it should be habitable. This is a Mars spectrum and the Venus spectrum, same one. Actually, as you know, Mars and Venus has absorption of CO2 like this, same position as the Earth, but they don't have the ozone, large amount of ozone, so no absorption here. That's way how to know without to go to Mars. How about this one? Is a spaceman observes Mars infrared emission like this, more detailed spectrum. Of course, this is the highest resolution spectrum on board the spacecraft. Very beautiful spectrum by PFS on board Mars Express. But still, CO2 and tiny H2O and CO dust absorption. But tiny, the minor constituents like methane and something like isotopes is difficult to identify such, even with such kind of high resolution, because spacecraft has a limitation, very strong limitation for the weight and size of the instrument. Yes?
Are the side lobe spikes on the CO2
Yes.
spectrum caused by the?
This one?
Yes. Is that the result of the varying frequency of vibration, the absorption of the energy over a wider frequency band that has spread it out?
Question is such kind of spikes indicates rotational or vibration state of the CO2. Actually, yes, and but almost these vibration, spike-like absorption is originated from the isotopes, CO2 isotopes, which has the same number of proton but a different number of the neutron. Maybe this is due to the low resolution. Such kind of individual line could never seen in this instrument.
Right, because it's interesting. We even see the center frequency null that would be expected at the bottom
Mm-hmm.
in the spread of the frequency that's being observed.
Yeah, actually, these large band is included plenty of CO2 absorption lines. But my instrument can't do that. Anyway, this is a most usual case. When we use a telescope, we see the summer emission from the Mars. At that case, emission from the surface goes through the Martian atmosphere, and after that, also goes through the terrestrial atmosphere. So what's happened? Like this. This two spectrum is obtained by most highest excellent instrument on board very large telescope at Maui. This is a terrestrial water vapor, and this is a Martian water vapor here. So if, of course, they are sophisticated to reconstruct a model about the telluric absorption, they could retrieve such kind of tiny Martian water vapor. But in fact, sometimes difficult to identify, and strongly depends on how to reduce the terrestrial signal. If we got the 4.5 times higher resolution, it should be more clear about that. but still on the shoulder of the strong absorption. So we always see the Mars signal behind the strong terrestrial absorption. High reserving power is required to distinguish the Martian signal from the terrestrial absorption. I think that's a problem. All of astronomers from the who observe from the ground. Methane looks more difficult because so tiny, 10 to minus 9 mixing ratio. And we have plenty of methane on Earth. So almost nothing signal at the bottom. And this is the signal of the methane. This is like this. Of course, they used appropriate method to reduce terrestrial absorption, but sometimes very difficult. And if we have a high resolution, it has also a benefit to detect sensitively, because low resolution got a smooth signal, which reduces the absorption depth, like almost a flat. But we have a high resolution, like this. We got a very clear absorption for individual line. That's what I want to do. So we need more reserving power for an absolute evidence for each species. So how about our instrument? Maybe almost done. Ultra high resolution, I said. This is a distribution of the existing instrument. This is our reserving power. This is a million. This is a kilo. And the vertical profile corresponding to the wavelengths. This is my instrument called infrared heterodyne. So we aim to improve 10 times or 100 times reserving power against the existing instrument. We aim the top of the world in this range. Actually, there are two groups already use this type of instrument for planetary studies. One is NASA Goddard Space Flight Center, and the other is from University of Cologne. They are my colleagues, and engineering works got together, and they had an outstanding finding. For example, the first detection of ozone on Mars from the ground has been done by this instrument, and the superrotation on Titan has first detected by this instrument. Yes?
There are no instruments on satellites that can do this detection?
Sorry, what's the question?
Yeah, on satellites,
Mhm.
are there any instruments that can do this type of?
Question is there any instrument? Is there any similar instrument on board the satellites? Actually, similar instrument has never gone to the space, but similar method in the radio range. I mean, the wavelength is a millimeter or sub-millimeter instrument is usually used on board the satellites to observe the terrestrial atmosphere. Yes?
Well, so based on what you just said, and the instrument is called the hetero for heterodyning. So you're heterodyning at the infrared frequency rather than a radio frequency heterodyning.
Question is, my instrument is infrared heterodyning, which is similar method in the radio heterodyne. Yeah, very exactly,
And
exactly.
Are you doing that at optic or at infrared frequencies, or are you measuring and then doing it with a Fourier transform or something algorithmically?
Okay.
Or are you actually doing it with a physical heterodyne
Uh-huh.
the way you would do with a radio frequency?
So shortly, your question is how to get the heterodyne in infrared. Okay, I'll tell you later. Yeah, I prepare slides. I prepare slides. It's real. It's real. That's it. That's it. Very simple. Very simple. Very simple. What I do is just to combine the signal from the telescope with infrared laser. I mean the local oscillator. Then what's happened? Beat signal has occurred very close to the frequency of laser. And yes?
No, go ahead. You'll
Okay.
probably
And the resultant intermediate frequency, I mean the difference between the laser and the signal, is now in the radio region. I mean some kind of down convertment, which keep the information of the infrared. But now we have the information in the radio range, very large wavelengths world, so very easy to cut, to resolve using the radio spectrometers.
So do you change the frequency of the QC laser and watch at each QC laser frequency where the beat frequency is on the heterodyne?
Question is, QCL or sorry?
Do you change
Did you
the
change frequency of the QC laser?
And as it changes,
As it
you
change, you
for the
watch
changing beat
for the change.
frequency in the heterodyne on the heterodyne.
The heterodyning, yes. By changing the temperature and the operation current, we can change the operating wavelengths, and then we monitor where am I by gas cell, a reference gas cell or something like that. Now we can see the position of the wavelengths. And I know the bandwidth of the instrument, then we expect the spectrum bandwidth we got. Anyway, the strongest point is this term is what I want to get, and this PL is the power of laser, very strong. So we can make the signal to increase by the appropriate power of the laser. And this is the expected spectra my students calculated, and this is the methane, and this is water vapor isotopes, which is also important to investigate the water cycle and the water history. And hydrogen peroxide is also important too, because they kill the organics. So it's also important for the sink of methane. But these species very tiny, 10 parts per billion to 100 parts per billion. But using my instrument, several days to a week operation is good enough to absolute detection for them. Of course, under the appropriate situation. This is a view of my instrument in the lab over there in the last measurements. This is a cube like 60 centimeter cube. We can say small, we can say big, but good enough to move on the summit. And to observe many molecules, we mount various Kyushu laser like this, and just to lead into the detector. That's it. Very simple. But you never see the infrared light, so sometimes difficult to. Anyway, this is ozone. Very beautiful, clean ozone spectrum above you. And you can also identify the very tiny ozone isotopes over there. Maybe using this, such kind of beautiful spectra, we can get a vertical profile over 10 kilometers above without balloons. So successfully operated at this institute and finished to set up as a summit in this week. And in the next week, it's so exciting we may achieve first light. So exciting. I have waited 5 years. And it's general talk. Now you know what is important for life. Stellar wind. I mean the solar wind in our case. And the magnetosphere and the dense atmosphere in the ozone layer, if possible, and organics alike, and water. And this part I could contribute using my instrument, but for extrasolar planets, we may need a very huge telescope at that time. Finally, I would like to emphasize the importance of the Haleakala. I mean the continuous monitoring at Haleakala. We also often use spacecraft data and of course use a very large telescope. But the spacecraft are limited by instantaneous field of view and spatial coverage, and also limited instrumental constraint, I mean the weight and size and mission lifetime, of course. And ground-based large telescopes are also difficult to provide long-term coverage, of course, due to the public offer. So when we want to see always, we need the dedicated telescope and a specific instrument. So using these two, we would like to achieve very unique results. And it would be, I hope, it's a pleasure, I hope it would be the beginning for a new collaboration between Maui and Japan. Thank you very much. That's all. Yeah, yes.
So I had a question. The 3 areas where methane was seen, was that by chance anywhere where previous landers or previous missions from Earth had landed? And if there were, could some microbes have grown for a while?
Question is, previous measurements of lander or other method could measure methane or some microbes. I would say one example of Viking. Viking actually installed to measure the organics. I mean the microbes, including microbes. But that sensitivity is very low. I mean, in my memory, 10 to 7 microbes per gram is the sensitivity of Viking. But in the ice of Antarctic and in the Atacama Desert, we have only 10 to 4 microbes per gram. If Viking landing at the Antarctic desert, they concluded no life on these planets. So that's why we, I think, brand new instrument, such kind of, I showed you the green spots image. Such kind of instrument should be over there. I think so. Sorry, over there.
Mars is usually not favorable for observation in its orbit. Does it matter? You're seeing Mars very small, very great distance.
Question is there problematic, or when we got the small Mars or small Doppler shift, you mean?
Like now Mars is far away,
Yes.
sometimes very close.
Yeah. Sometimes close, sometimes far away. It depends what do you want to do. For example, this is spatial resolution in the worst case of 1.8 meter. This is another telescope which we're going on to build on the summit between the Tohoku and the UH. This is a far case. At this point, my instrument field of view is here. So maybe here to here is a 6,000 kilometer. So maybe one axis correspond to the 100,000 spatial resolution. So if you need more spatial resolution, we should close to the Mars. But if you want to detect the methane, it's more important to get large Doppler shift. I mean the relative velocity between the Mars and Earth, because we want to know to Martian signal far from the terrestrial methane absorption. So if we got the very large Doppler shift, we can get the high transmittance of the signal. So it significantly improved the signal to noise ratio. So that depends how what we want to do. Okay, so sorry.
How much does the instrument you showed us on the table in that 60 centimeter cube cost?
Yes. Wait. Actually, I plan to put here, but fortunately, my schedule is somehow on time, so now it's on summit. But maybe like this. Actually, this is in the 60 centimeter box, and my one of the advantage of this instrument is spectral resolution is doesn't depends on its size, because what I have to do is just to combine the signal. It's very different from the grading type and the Fourier transfer interferometer. If they want to have a similar resolution as I have, they have to prepare 3-meter running Fourier transfer spectrometer or 1-meter very huge gratings. That's one of my most advantage.
My question was, how expensive is it?
How expensive?
Yeah, how much does it cost in dollars?
Okay. Wait. My instrument very cheap, very cheap. Yeah, it's real. It's real. It's real. Except for 2 parts. Except for 2 parts. Most expensive part is this one, this blue guy. This is a dual vessel, and we have something like a 100 micron detector inside the vessel. I don't know, but the people who can make this type of MCT detector is only one in the world. In the grand gentleman, already retired from the, how to say, some company to, I don't know how to say in English, but Raytheon company to make the missile rockets or for some yeah, other stuff from this one. Because, of course, they can make many about this type of this instrument. But, okay, anyway, price. 60,000, yes. Sorry, I'm not familiar to translate the, yeah, $60,000. This one is very so expensive. And once he has died, nobody provided me. So that's problematic. So NASA should be, how to say, keep such kind of technology. I hope. I really hope. I think it's, other part is not so. Yeah. Yes.
Do you know of any mathematical models that would indicate that there might be microbes or life on Mars?
No idea. Because sorry, no idea. So question is there any mathematical calculation to confirm the microbes existence or something like that? No. Sorry for that. Yes.
Since the polar ice caps
Mm-hmm.
seem to have
Mm-hmm.
much more water
Mm-hmm.
on the surface,
Mm-hmm.
would that be a likely place to look?
Yes, I completely agree with you or suggestion. And actually, there are amount of water ice, of course, accompanied with carbon dioxide ice. But now that's why we try to observe water vapor isotopes, because still nobody knows how much amount in the polar caps and where that should be gone after evaporate, and how to condensate after that. So maybe we have still things what to do from the ground, but we should go, of course, around the polar caps. Yes.
We've heard in the news within the last year or two about two different Mars projects.
You had 2 projects
Yes.
of Mars.
The one they talked about, a middle-aged couple that would just go to Mars and boomerang and come back, and then there's the
So
project that's
what-
talking about
One is
using people in
to go to
reality
Mars.
TV, and they would actually
Okay,
go to Mars.
okay. Go ahead, go ahead, go ahead.
Point of view about this. Is it pure theatrics, or is there any credibility?
I don't know. Question is, yeah, as more public offer, I mean the TV, and how to say, more other aspect to go to Mars.
Too private. Business.
Yes, yes. It's true. I don't know.
Are you going?
Maybe after the other guy is going, and after confirming the safety, then I'll go. Maybe you can go. I recommend. Thank you so much. Thank you so much for many questions.